Thank you very much for inviting me here. I landed yesterday at 8:30 and it was raining, and that made me realize why you probably invited me from Seattle. So you can thank me for that, although it didn't last very long. I'm sorry. So my laboratory's mission is to determine modifiable factors in children's early environment that can positively impact their cognitive, social, and emotional development, and to develop actionable strategies to optimize them. So simply put, I spend my day studying what you do and what you teach, and I'm here as much to learn from you as to share what I know with you, because all of us are trying to do this. It's a mission that I think all of us here share. So in the 3 hours that I have today to talk to you, I'm going to focus only on the one of the three that I talk about, cognitive, social, and emotional, and we'll focus today on early experiences in children's cognitive development. And in particular, I want to focus on one part of cognitive development, what developmental psychologists call executive function. And executive function has three core components. The first is what's called inhibitory control. And inhibitory control basically is a child, an infant, a grown-up's ability to avoid distraction, to be able to inhibit competing impulses so that you can focus on something in front of you. Working memory is a second component, and that has to do with your ability to hold something in your mind while you think about something else. So essentially having two things going on at the same time in your brain. And the third is cognitive flexibility, which is your ability to apply something you've learned from one task to another. And you see this start to develop actually in very, very young babies, where they start to make a connection with something they did in one arena and applying it somewhere else. But of the three of these, the one I want to focus on today is inhibitory control. And I'll try to make the case for why I think it's the most important of all of these. Not that the others aren't important, but inhibitory control is extremely important, and it's particularly now under threat for this next generation. So here's an example of inhibitory control. The simplest solutions are often the cleverest. They're also usually wrong. So it says find X, and the person says here it is. This desire to jump to a conclusion is part of what's lacking inhibitory control, right? Not spending the time to think out what the right answer is, just instantly jumping. Okay, now, most of you all know about how brain development happens. Here's a graphic of it. This is the back of the brain here, and this is the front. And as it darkens blue to purple, that's how development progresses. It starts from the back, and it goes to the front. And the very front part here is where the cerebral cortex is. That is the sort of executive section of the brain. That is where executive control ultimately resides. I'll show it to you in another graphic. Here's the brain, and here's the back of the brain, and here's the front. Here's the frontal lobe where executive function operates. And at birth, as you know, children already have their brainstem. They can do vital functions. They can swallow. They have their cerebellum pretty well intact, so they can have smooth movements and coordination. They have audio and visual processing. That's back here in the occipital lobe. Now, at about 4 months, they develop sensory and motor integration and the inhibition of primitive reflexes. So you know what the primitive reflexes are of the brain. You know how babies have the startle reflex. It's about 4 months that they start to be able to suppress that with the development of the parietal lobe. At 10 to 12 months, it's deep in here. You see the development of the limbic system, and that's where emotions reside. So that's why 4 to 6 month olds can't have temper tantrums, but 15-month-olds can have very, very good ones. They have a very, very well developing emotional center, sometimes too rapidly developing without a lot of inhibitory control, so they can very easily become overcome with emotions. At 18 to 24 months in the temporal lobe, we see the processing of sound and language, and that's when we start to see an explosion in children's use of words. And finally, from early childhood to adult is the frontal lobe where I talked about, where you have abstract thought, reasoning, judgment, and the regulation of emotion. This is sometimes called sort of the CEO center of the brain. It's the most important in many ways, and it takes the longest time to develop, but the development starts very, very early. Now let me give you an example of that. Some of you may be familiar with the Stanford Marshmallow Test. So this was really was kind of started as just an observational study of about 25 to 30 years ago, where researchers brought preschool children, 3 to 5 years old, into a room, and they asked them to choose a treat, one of them was a marshmallow, and they said that they could have one marshmallow now, or if they waited 5 minutes, they could have 2 marshmallows. And they left the marshmallow on the table rather, and the researcher left, and the child was being filmed, and they came back 5 minutes later, and true to their word, if the marshmallow were still there, they got 2, and if the marshmallow wasn't there, they didn't get another one. And they analyzed the videotapes and watched these kids. Now, the videotapes themselves are hilarious because some of the kids are trying to look away, to not look at the marshmallow, knowing that it was too tempting. Some of them bite their fingers. Some of them take a little pinch of the marshmallow. And many of them just break down ultimately and eat it. About 20% of kids are able to stay in the whole 5 minutes and not eat the marshmallow. But they waited different amounts of time before they ate it. And when these kids were followed 25, 30 years later, the longer they waited to eat the marshmallow, the better they did in school, the higher their graduation rates, the higher their incomes were. It goes beyond that. The lower the risk of committing crimes, the lower the risk of alcohol and drug problems. So this ability to inhibit the impulse to eat the marshmallow is vitally important to long-term success, and it starts in early childhood. I'll give you another much better studied example. This is a study from New Zealand. Many of you may be familiar with the Dunedin longitudinal study. This was a birth cohort study. They followed 1,000 children from birth. Now I think they're in their 30s. There have been thousands of papers published on it because it has excellent controls and fantastic follow-up. Now here's what they found. What you see here is childhood, what they called self-control in quintiles, from low all the way over here to high all the way over here. And I've shown you just a few things. If you look here in yellow is substance dependence. So as self-control goes up, adult substance dependence goes down. Here, poor physical health, again, the same relationship. And socioeconomic status, the opposite relationship. The better self-control, the better socioeconomic status you have as an adult. I just chose these 3. You could pick anything, and you'd see the same relationship. And the one thing I want you to remember, and we'll come back to it in a minute, is there's no threshold here, right? There's no magical number. The better self-control children have in childhood, there's a linear relationship. It's better over their entire lifespan. Now, all of this starts very, very early. You all know I don't have to tell you that early experiences matter, but we'll talk a little bit about why they matter and how. So this is a typical newborn brain, and it weighs 333 grams. And in the first 2 years of life, it triples in size to almost a kilo. It's an extraordinary period of brain growth that you all are involved with. In fact, it's really unparalleled over the whole lifespan. So you can see here in this graphic, brain growth over the lifespan, and look at how steep it is early. And it really doesn't peak until the early 20s. That's actually when the frontal cortex is fully developed. And then I can let some of you in the room find yourselves over on the right here and see why you had such a hard time finding your car keys this morning. But the point is that very early experiences dramatically impact brain growth. Now, we're born with a lifetime supply of neurons, of brain cells. That's not what actually grows. It's the connections between them, what we call synapses. And those form based on early experiences. Every experience a baby has creates one of those connections. If you will, the mind is fine-tuned to the world that babies inherit. And to give you an example of that you can all relate to, any child born anywhere in the world can learn to speak any language fluently. But if she isn't exposed to certain sounds early in life, she can learn to speak a language fluently later, but she'll never sound like a native speaker. So a baby born today in mainland China can learn to speak Mandarin fluently, amazing as that is, because it's an incredibly difficult language. But if she doesn't hear r sounds early in life, she'll never be able to make that sound later. She can learn to speak English, but she'll never sound like a native speaker. We all know people like that. It's not because she wasn't born with the capacity to make that sound. It was because she was born into a world where that sound didn't exist, and during that critical period of brain development, she never developed the capacity to make it. So I'll show it here schematically. Here are the brain cells present at birth with the synaptic connections, and at birth, each brain cell has about 1,500, so each brain cell is connected to about 1,500. By 3 years of age, each brain cell is connected to about 25,000 other brain cells. And then starting by about 15 years, you'll see there's a gradual pruning of pathways that aren't being reinforced. But some of those pathways, many of them, last for a lifetime. I don't know the last time many of you rode a bicycle. I went 25 years without riding a bicycle, and just as they always say, it's something you never forget how to do. Remember how hard it was to learn how to do that? Remember how difficult, how almost, and those of you who tried to teach children, it's a miracle that they ever can learn to do it. But once learned, it never goes away. That's an example of sort of the long-term memory, muscle memory in that case, that happens very, very early in childhood. Just how early is demonstrated by this. Now what you see here is the breathing pattern of a one-day-old infant listening to music. And you can see here that Mozart is playing and it's eliciting this kind of a breathing. And then Stravinsky is put on, and then Mozart comes back on. Now I show you this not to present some kind of an infantile critique of classical music, but some of you might have a hypothesis for why Stravinsky did this poor child's breathing. I show this to you to show that there is a demonstrable, discernible physiologic response to what babies are hearing from one day of life. This child is distinguishing between one type of music and another. It's affecting them. That's how well tuned they are. So all of those experiences matter. All of them have lifetime effects. What you see here is a game from Habits of the Mind. It's called Walk the Line. Some of you may be familiar with it. Maybe some of you do it in your toddler classrooms. It's a very, very simple game. You basically take a piece of tape and you put it down on a rug or a carpet, and you ask the child to walk the line, to put one foot in front of the other. Very, very simple. But keep in mind that to do that, he, in this case, has to not be distracted by what's going on in the classroom. He has to focus on what's in front of him. And this is level 1, right? You can make the line longer, you can make the line have curves, and the more you do that, the more and the longer he has to stay focused and develop that kind of inhibitory control so that he can stare at the marshmallow and not stuff it in his mouth. Now, we know from decades of research that too little stimulation early on during this critical period is very, very bad for brain development. What you see here are 2 PET scans. Now, PET scans are a fancy way of measuring brain activity. The brighter the color, the more brain activity there is in that region. And on the left, you see a PET scan of a normal kindergartner. And on the right is the PET scan at kindergarten age of one of the Romanian orphans. I don't know how many of you are familiar with Romanian orphans, but these were children who were profoundly neglected during early childhood, essentially grew up in closets with virtually no visual, emotional stimulation. And there are areas, as you can see, of this poor child's brain that didn't develop at all as a result of that profound lack of stimulation. So too little stimulation is clearly very, very bad for brain development. But one of the questions we've had in our lab for some time is, what about too much stimulation? Is it possible to overstimulate the developing brain? Or more appropriately, is it possible to inappropriately stimulate the developing brain? Are there good kinds of stimulation and bad kinds of stimulation? And are there the right amounts and the wrong amounts? So this says, go to your chat room. Now we've been technologizing childhood in a way that's unprecedented. In 1970, the average age at which children began to watch television, traditional media, was 4 years of age, like this cute little girl. And today, it's 4 months of age, based on research that we've done in my lab. Now, it's not just that they start watching that early. They spend a lot of time with it. So you can see here that children 0 to 6 spend about 2 hours a day with media, and children 8 to 18 spend about 5.5 hours a day. Don't ask me how much time 7-year-olds spend, because I didn't collect these data. They were somehow left out of the... But this is based on how much TV children watch at home, and as you all know very, very well, most children are somewhere else during the day. They're not at home. This is home viewing, and so we did a study a few years ago of child care centers to find out how much TV children are watching in child care centers. And here's what we found. We found that at center-based programs, sort of institutional daycares, children watch about 20 minutes a day. But at home-based daycares, where about half the children in the United States are taken care of, and unfortunately a disproportionate number of low-income children, they watch an additional hour and 20 minutes a day. Now, when you put all of this together, what you find is that the typical preschool child in the United States spends 4.5 hours watching TV. And they're only awake for about 12 hours. So they're spending about 30% of their waking time in front of a TV. Which brings us to Baby Einstein. Now, how many of you are familiar with Baby Einstein? Most of you, okay. So this is Baby Einstein, Baby McDonald, A Day on the Farm. It's for infants 9 months and up, but they have them for as young as 2 months. And I'll show you here a random 20-second segment from Baby Einstein so you can get a sense of what it's actually like. So in that 20-second clip, there were 7 scene changes, about 1 every 3 seconds. It's the most exhausting day on the farm since John Steinbeck's Grapes of Wrath. And it's nothing like a real day on the farm, right? Those of you who are watching it were trying to make a coherent narrative out of this. And there is no coherent narrative. It's completely random. But babies watching it aren't trying to make a coherent narrative out of it. They're not cognitively capable of it. What's keeping them looking at the screen is all of that stimulation, is all of that unnatural stimulation, since that's not the way being on the farm actually is at all. So I want to switch for a little bit and talk about the rise of ADHD, or attentional deficit disorder. It currently affects about 10% of children in the United States. And it's 10 times more common today than it was 20 years ago. Now, we've known for a long time that there's a genetic basis for ADHD, okay? Here I summarize a variety of studies that looked at how heritable ADHD is, and if you put them all together, it's about 75%, okay? What does that mean? That means if one identical twin has ADHD, there's a 75% chance that his or her sibling will. Now, if it were entirely genetic, it should be 100%, because identical twins are genetically identical. So there's clearly something else that plays into this. And not surprisingly, like many things, when we talk about nature and nurture, it's really a combination of both. It's always been a silly dichotomy. There are a lot of genes that play a role, there's an environmental component to this, and they come together to create ADHD. The Surgeon General himself said for most children with ADHD, the overall effects of these gene abnormalities appear small, suggesting that non-genetic factors also are important. But I want to take it a step further before we talk about what those might be, and you probably already have some sense of where I'm going with this. I actually think that the focus on ADHD misses the point. And here's why. ADHD is a clinical diagnosis, and like many clinical diagnoses, like most clinical diagnoses, there's a normal distribution, okay, of symptoms. And we draw, as clinicians, a line, and we say, okay, you're on this side of the line, you have ADHD. We diagnose you, we medicate you, we think about changing your environment, etc. But there's a child that's on this side of the line, right, who clearly has problems with attention and doesn't meet a clinical diagnosis. Now remember the graphic I showed you about self-control in quintiles. There was no threshold there. Our goal as early educators and as parents is not to just try to avoid having a kid with ADHD. Our job is to try to maximize every child's ability to develop their executive function, their inhibitory control, because that pays dividends over their entire lifetime. And that's why, for me, what we need to focus on is those kinds of activities, things that really promote that. Now, we had for some time what we call the overstimulation hypothesis. And what that says, quite simply, is that prolonged exposure to rapid image change during that critical period of brain development would precondition the mind to expect high levels of stimulation, and that leads to inattention in later life. So to put it another way, you watch enough Baby Einstein Day on the Farm as a baby, and then when you go to the farm, when you're a school-age kid or a toddler, it's boring. Nothing's happening fast enough. How come we have to walk from here to there? How come there's no marionette suddenly bouncing back and forth? Right? You've developed an expectation for something that doesn't really exist, a level of input that's supernatural, that's unnatural, that doesn't occur. And we tested this some years ago, and what we found was that the more television children watched before age 3, the more likely they were to have attention problems at age 7. Now, the other thing we found was that the more cognitive stimulation they received before the age of 3, the less likely they were to have attention problems. And cognitive stimulation was measured by how often kids were read to, how often they were sung to, how often they were taken out on outings, to museums, to zoos, etc. Specifically, for each hour of TV that children watched before the age of 3, their chances of attentional problems were increased by about 10%. And each hour of cognitive stimulation reduced their reduced their attentional risk by 20%. So to put it another way, a child who watched 2 hours of TV a day before the age of 3 would be 20% more likely to have attention problems at age 7 compared to a child who watched none, right? And cognitive stimulation had the opposite effect. Now, if you will, these are two sides of the same coin. There are certain things that we can do early in children's life that impact their cognitive ability, their attentional capacity, their inhibitory control positively, and things that we can do early that impact it negatively. Now, to test this again, to test whether or not in fact it was really the rapid image change, we had a hypothesis that what children watched might affect it. Content might in fact be key in determining this, whether there's truly a link between overstimulation and attentional capacity. So I want to show you two examples of content. The first is from the Powerpuff Girls movie. Have any of you seen that? Okay, so this is the opening sequence to the Powerpuff Girls movie. And again, you'll notice the rapid image change. So that's the opening sequence. This is the first movie that was ever rated PG for non-stop frenetic animated action. I'm not making it up. That's the back of the box. I want to contrast that with something I know you've all seen, regardless of your age, and that's this. And here is here's a segment from Mr. Rogers.
Hi, Owen.
Oh, hi,
How are you?
Fred. I'm fine. How are you?
Good, thanks. I brought my television neighbor to see what a restaurant was like.
Oh, I'm so glad. Can I show you to a table?
Certainly.
I'm awfully busy today. One of the waitresses is ill.
I see.
So I'm sort of doing double duty. How about this?
This is fine. Thank you
Grand.
very much.
Sit down and I'll be right back.
All right. Now, when you come to a restaurant, usually somebody shows you what table you're supposed to sit at. And one of the first things you do is to put your napkin either on your lap or up here. And then, well, this is the way a table is set.
So Fred Rogers invented reality TV. He's not given credit for it. Actually, it's not reality TV, right? I mean, the waitress says, I'm awfully busy today, but she doesn't seem the least bit hurried. Everything happening here is happening certainly by today's standards, at a really slow pace. It's actually soothing to watch this, and it feels very much like you're there, like he's speaking directly to you. So when we looked at what children watched and the risk of attentional problems later in life, we found that children who watched educational programs like Mr. Rogers, not like Baby Einstein, which is not educational, had no increased risk of attention problems at school age. Children who watched entertainment shows like the Powerpuff Girls movie had a 60% increased risk of attentional problems. And children who watch violent programs, which I didn't show you, I don't particularly like to show them, but those are even more rapidly sequenced typically, had an over 100% chance of having attentional problems later in life. So this seems to build more credence that there is a risk of overstimulation, of too much unnatural kinds of exposures. Mr. Rogers much more simulates real life, Powerpuff Girls not at all, and other types of content even less. Now, what I've shown you is all observational studies because thankfully I can't in my lab in good conscience bring babies in and overstimulate them for a long period of time and then look at what happens. So we've been building a mouse model of overstimulation, of TV viewing, if you will. And what you're seeing right now is mouse TV. So it's kind of annoying, actually, but that is audio from the Cartoon Network, just to be cute. Obviously, the mice, as far as I know, don't know what the Cartoon Network is saying. And we put them in chambers, in sort of TV viewing chambers, and the lights are around there, and there are speakers on top, and the lights are photorhythmically activated by the speakers. So this is mouse television, and they start watching at 10 days of life, and they watch 6 hours a day for 42 days. It's basically, they spend their entire childhood watching TV. I know it's sad, I apologize, but some children do the same thing. And then 10 days later, we assess their behavior. Now, because these are mice and not children, we can do real experiments. I can have half the mice watch TV and the other half not, and we can measure differences. And we do it in a variety of ways. I'll show you the first thing we do is we measure activity and risk-taking. And we do this using what's called the open field test. Now, here's the way the open field test works. You put a mouse into a black box, which is an open field. We're simulating it. And you see this electrical tape here is the middle of the field. And mice have very few friends in the natural world. They tend to not like being in the middle of an open field, and they'll naturally stay around the periphery. But of course, they have a competing instinct to forage and to explore, so they will venture a little bit into the middle. And what we do is we exploit the fact that we have a white mouse on a black background. We have a computer tracking program that tracks the mice, and we look at how they move. And you look here at this mouse, and you'll notice that she, I'm not sure what it was, spend most of their time around the periphery, as you might expect, and a very little bit of time in the open field. Now look at this mouse over here. You might notice a couple of things. One is that it spends a lot more time in the middle, but it's also running around a lot more, right? So this mouse would be sort of hyperactive and non-risk averse, willing to take a lot more risks, okay? And when we compare our control mice to our overstimulated mice and look at how much time they spend in the center, you'll see there's dramatic differences with the overstimulated mice spending a lot more time in the center, and they enter the center a lot more than the control mice. So they're both hyperkinetic and risk-taking compared to normal mice. Now the next thing we do is we look at novel object recognition, and this sort of tests short-term memory. And the way you do this is we put the mouse back in, and we give it two objects to explore. And mice will explore objects. They're always curious what they're there for. And they'll spend their time exploring both of them. Then you take the mouse out, and you substitute one of the objects for a novel object. Not dissimilar, frankly, to what you might do when you're playing with young children, right? They will develop more of an interest in something that's novel than something that they've become familiar with and bored with. And that's what you expect with mice, too, that if they remember something, they will spend less time on it. And we track them exactly the same way as we did before. And you can see that this mouse is spending more time on the novel object than on the familiar object. And this mouse is spending about equal time on both. And here's what we found. For the control mouse, they spend about 80% of their time on the novel object. So they remember which's new and what's not, and they spend more time on the novel one. But look at what happens to the overstimulated mice. No difference at all. They spend the exact same amount of time. So it's as if they don't remember the novel object or they don't care. But somehow, that overstimulation has made it impossible for them to remember what's new or what's novel. Or they're just not interested. They're not interested in the novel. And the final test we do is what's called the Barnes, or the final test that I'll show you is the Barnes maze, and this tests learning. And the way you do this is you put a mouse on a demi-sphere like this, and there are 18 holes, all of which are plugged except for one. And you shine a bright light on the mouse, and which the mouse is not going to like. I told you they don't like to be out in the open, and it's going to try to escape. And you measure how long it takes to actually exit, to find the escape hole over 5 successive days. And here you see it. You notice this is on day 5. And you'll notice the mouse sort of gets its bearings without exploring every hole, and then quickly makes the line for the exit. Now, when we test them over successive days, you see the control mice here and the overstimulated mice here, and how long it takes them to actually escape. And on day one, the overstimulated mice actually escape faster. They find the escape hole faster than the control mice. Does anybody have a hypothesis for why that might be? Exactly. They're the ones that are hyperkinetic. So you put them on and they start running all over the place as fast as they can. If there were ever a good reason to have attentional disorders, it's if you're put in a room and you only have a certain amount of time to get out. Don't waste your time thinking, just start looking right away. But you'll notice that over time, actually, what happens is that the control mice do better. So they're better learners over the long term, although they're less hyperkinetic at the beginning. Okay, I mentioned that we can't overstimulate children ethically, but we can try to provide the opposite, the right kind of stimulation in an experimental way. And we did a few years ago what we called the building block study. This was an experiment, a randomized trial in a Seattle clinic. We took 200 kids, 18 to 24 months of age, and we gave half of them blocks, big blocks, mega blocks. Actually, they're kind of like Duplos. They're Duplo knockoffs. Half of them got them at the beginning, and half of them got them at the end. And their parents got what we call blocktivities. So this is how to play with kids with blocks. It's stuff that you all know and you all do. Very simple things. Sort the blocks, stack the blocks, count the blocks. And I should mention that these were low-income parents. So the things that come quite naturally to a lot of parents, especially educated ones, don't necessarily to ones who aren't. We found that in the kids who got the blocks, 59% played on a typical day, compared to 13% of the ones who didn't get blocks. So giving the kids blocks made a difference in how often they played, presumably because a lot of these kids didn't have blocks to begin with. They played with them for about 20 minutes a day, about 1.5 episodes a day, and about 65% of the time it was with a parent. And then 6 months later, we looked at their language. How well was their language developing? In the control group here, the kids that got the blocks late, they scored in the 42nd percentile, okay? So below average, but unfortunately not uncommon for low-income children. But look at what happened to the block group. They actually scored slightly above average and significantly better than the non-block kids. So getting the blocks, and more importantly, the blocktivities that go with them, really help promote language in these low-income children. Why might that be? What does block play do? You probably already know it does a lot of things, but one of the things that it prevents is something that television does, and TV or media displace talk. I want to put this in the context of what's called joint attention. Joint attention, as the name suggests, is two people focusing on the same thing. It begins with simply a shared gaze, as you see in the upper left-hand corner. And starting at about 6 to 9 months of age, children's attention can be directed at something, okay? And then they will look at the object, or whatever it is, and they'll instantly turn back to their caregiver, okay, and say, what is that? Tell me something about that. Some people call it serve and return, but the real point here is that in the course of interacting over a day, this happens thousands of times. Parents are directing babies' attention, babies are looking, coming back. Starting at about 9 to 12 months of age, the child will actually initiate triadic shared gaze, as you see up here with the young toddler pointing to something, getting mom to look at it, and then they're naturally going to look back towards each other and have some kind of an exchange about it, all right? As I said, this happens thousands of times a day. Most people aren't even aware of it, but it's vitally important, not just to children's social development, but to their cognitive development as well. Now, we studied a while ago the impact of having a television on, and we did it by using what's called the Lena system. This is a small digital recorder. It's worn in a vest, and it records everything a child says and everything that they can hear, right? It's recording everything that's audible on their chest. And there's a special software we use that decodes it, and it can analyze it in terms of adult words, male and female, child vocalizations, conversational turns, so how often is there that back and forth, that serve and return, and it can also pick up television and tell us how often the TV is on. And the way we do these analyses is what we call conditional regression. So we actually, each child served as their own control. We compare times when they can hear a TV to times when they can't hear a TV and look and see how many adult words they hear. And what did we find? Well, each hour of audible television that a child that was recorded at their chest resulted in them hearing 656 fewer adult female words. Now, how many words does a typical adult female say in an hour? No one wants to hazard a guess. She says about 730. So there's about a 90% displacement. When the baby is hearing TV, she hears 90% fewer adult female words. Now, when the TV is on, they hear 200 fewer adult male words. Now, how many words does a typical adult male say in an hour? So I give this talk all over the world, and there seems to be universal acceptance, this is primarily a female audience, in what's truly a myth, which is that women speak less than men do. Typical adult male says about 725 words an hour. So men and women say the same number of words an hour. Doesn't mean they listen to each other, but they say the same number of words. The reason you're seeing less displacement here is not because men speak less than women, but because men speak to babies less than women do. So this is still a 90% displacement in the number of words that the father or the adult male caregiver would say to the child, because they don't talk as much to the baby. They're talking to the television instead. So that's why you see that difference. So having a TV on reduces that. Now, in today's world, I would say that one of the other things is not just the TV, but it's this thing. Having this thing on you reduces the number of words that a child is going to hear, because it's incredibly distracting in the same way that a television is distracting. In fact, in many ways, it might even be worse because it requires more of your cognitive capacity to attend to it. Okay. I want to talk about some of the other experiments we're doing. This is looking at neuroendocrine effects. So this is basically brain hormone responses to different types of stimulation. And what we do here is, or what we did here was an experiment. We brought about 50 babies who were 9 to 12 months of age into the lab, and we randomized them to either play with blocks for half an hour or watch a Baby Einstein DVD. And we collected salivary cortisol on them, so serially, which is basically collecting saliva. Babies love to donate saliva. It's very easy to get them to comply with this. And salivary cortisol measures kind of serum cortisol, but it lags about 20 minutes behind. Now, most of you think of, or if you're familiar with cortisol, most of you think of it as a stress hormone. And it is actually a stress hormone, but its relationship to learning and to cognition is fairly complicated. It has what we call an inverted U. So your performance is measured here, and your arousal or your cortisol level is here. And at very, very low levels of cortisol and very, very high levels of cortisol, you perform at your worst. There's a right amount, right? So if you're taking a test and you're super stressed, you're not going to do your best. And if you're super laid back, right, super chill, as they say today, you're not going to do your best. There's a right amount of quote-unquote stress. There's a right amount of cortisol, which is really much more a measure of the fact that you're cognitively engaged in what's going on. You've activated your brain, okay? Now, the problem is that we don't know what the right level of infant cortisol is, right? There's no standards for that. And that's why in this experiment, we randomized babies to do something that we already knew was good, namely block play, because we know it's good anyway, but we had already shown it improves language, versus baby DVD viewing, and look to see what were the differences. So we know one is whatever cortisol level is achieved during block play is good, and we'll see if it's different. And in fact, block play was here, and baby DVD viewing was significantly lower. So sitting there passively watching a TV program like Baby Einstein does not engage the brain in the same way as playing with blocks. Now, why might that be? What is the one thing a child never says, or for our pre-verbal children, ever thinks when they're sitting there watching a baby DVD or a TV program of any kind? I did it. They never say that. They never think that. It doesn't, in fact, ever happen. It's not possible. And that I did it response is huge. And it's elicited all of the time. Most of the time, you're probably not even aware of it. It's registering to them that something they did made something else happen. And that brings us to this, And I promised Deborah I would talk about this since I've been in the news lately around my thoughts on this. So there are a lot of apps now that are being propagated for very, very young children. And I want to point out something that is obvious but surprising, which is that the iPad is exactly 4 years old. It was invented 4 years ago in April. It's kind of remarkable because most of us can't even remember the world pre-iPad. It seems like it's always been here. But it's only been around a very short time. And unfortunately, for those of us that try to study the impact of various things on young children, 4 years is not very much time. We don't have as much data as I would certainly like to have. But I want to share with you my thoughts. Now, to give you some sense of the landscape, there are now 75,000 quote-unquote educational apps at iTunes, and 35,000 of them these are free. So you can be quite confident that thousands, hundreds of thousands, millions of parents are downloading these for their very, very young children. There are 48,000 developers currently developing educational apps, and there have been, in fact, 3 million downloads of the Fisher-Price apps in particular in 2012. Now, the Campaign for Commercial-Free Childhood, which has used our research in the past to argue with the FTC, in fact, they were part of what used our research against Baby Einstein to try to get them to stop making educational claims, have argued that there should be a stop, people should stop marketing these as educational, which I, of course, agree with. But the real question I have, and you should have, as we try, before we have robust data, to think about what these apps are and how we should visualize them, is on a continuum. So over here we have kind of what you might think of as traditional toys, traditional interactive devices. And over here we have what we all know as the television. And the question is the iPad more like this, more like a television, or more like traditional games? And to be clear, it could be nothing more than a television. You can just watch something on an iPad, in which case I would argue it is a television. It's just a portable television. But you can do different things with it too, and I think those have to be acknowledged. Now I want to sort of focus on several features of toys or devices and compare, if you will, kind of a traditional toy like a Jack-in-the-Box, an iPad, theoretically an iPad game, an iPad app, and a TV. So the first is this device reactive? Meaning, when the child does something, does it do something in return? Can the child get the "I did it" response from it? Well, clearly that can happen with a Jack-in-the-Box or a toy like it. And it clearly can happen with an iPad. It clearly cannot happen with a television. The second is it interactive? Can the toy itself, without an adult present, prompt something in the child? Can it take what the child did and give back a specified, tailored, unique response to get the child to do something? Well, there I would say that iPads can do that, and traditional toys typically don't. Can it be tailorable? Does the toy itself function differently depending on who the child is, how they're playing with it? Again, I think iPads can do that, and these other things cannot. Is it progressive? Again, without adult supervision, without a caregiver there, does it move a child along a continuum? Again, I would say that the iPad technology could conceivably do that, and these other things could not. Now, can it promote joint attention, which we talked about before? Clearly, traditional toys do, iPads do, television does not, as we've shown. And then, is it portable, which is, for today's parents, a very important thing, and you can see that here. Now, before anyone takes away from this that Dr. Christakis thinks that iPads are the best thing to come along, I should point out, three-dimensional. Toys are, I should have said this, toys are three-dimensional, iPads are not. But before you look at this and say, Dr. Christakis, by the check marks, it looks like iPads are better, I should point out that the simple act of reading to a child accomplishes all of these. And I don't want to suggest for 1 second that there's anything better than reading to a child, than playing with a child. There clearly is not. But I do want to point out that there are very real differences between traditional passive media, which I would argue has no benefits for infants, and well-designed interactive apps that at a minimum might be harmless, and particularly if they're displacing TV, would be sort of from a harm reduction approach better. So if you ask me, would I rather a child watch half an hour TV Baby Einstein or play with an interactive app? If that's the choice that's before them, I would argue that it's better off that they spend the time with the app. Not better than being read to, but better off than the alternative. Now, there's a problem with these too, at least theoretically. I want to share that with you. There's what's called the dopamine reward pathway in the brain. And without getting too technical, there's a ventral tegmental area in the brain. And that sends a signal to the nucleus accumbens when there's pleasure involved. That sends dopamine to there. And that's perceived in the brain as very pleasurable, as a reward. And that area of the brain then sends a signal to the prefrontal cortex, the sort of executive section of the brain, that says, that was good, I like that, do it again. Use your executive ability to make that happen again. Okay? That's the feedback loop. It's a generic dopamine reward pathway. It's activated all the time. Everything from eating something pleasurable, drinking something pleasurable, being told something pleasurable activates that reward and signals to the higher parts of the brain, that was good, I want it. And of course, we use this as part of our educating young children all the time. They want praise, they want reinforcement, and when they get it, when they get the kind of feedback they like, it encourages that behavior to get it again. Many of you may remember B.F. Skinner. This is what he basically relied on, was a dopamine reward pathway where rats were given rewards for reacting to lights, pushing the lever and getting food. And he showed very, very well how you can make a mouse essentially very responsive, even addicted to pushing a particular lever. This is what he did then. If he were alive today, this is what he would have. Now here's a toddler sitting on a high chair holding a tomato. What do you think that he is going to do with that tomato? He's going to drop it, I think people said. Yes, he's going to drop. There's 95% chance he can take a tomato, he's going to throw it over the edge there. And if there's someone in the room, that person is going to go pick up that tomato and put it back. And the child will be delighted by it. We've all seen this. We've seen it a million times, right? There's the dopamine reward pathway. That's the I did it response. I threw the tomato, I dropped the tomato. First I saw what gravity did to it. Then I made this person come over, pick it up, put it back in front of me. Ha, ha, ha. And as you know, it will go on forever. I mean, it's never been tested, but you know, if there isn't some other intervention, this will go on forever. So delightful is that reward pathway, that I did it response. And that is, I think, a very real concern about these devices, because there is the opportunity for the constant I did it at no physical expense. It's the child who gets to throw the tomato off infinitely and have it brought back. Okay? I think that is a very real risk. And that's at least one of the reasons that there have to be very serious limits placed on usage. But I want to show you that, you know, there are different types of uses, and as you think about how parents and how you might even counsel them if they are using them and if they don't take your advice to not use them to heart, that they should recognize, and you should recognize, that there are differences. I mean, imagine this and think about what that experience is like. Or this. I mean, what you're seeing is a lot of traditional ways of playing, books, coloring, that are now available in a digital way. Are they better? No. Absolutely not. And they're more expensive. But I think we have to think of them as being more like those activities than purely watching passive media. And you see other examples here as well. The point being that the children are in this highly technologized world. We're seeing an evolution. We don't have much control over it. I can tell you that we've done a lot of studies trying to reduce media exposure in young children. They're painful to do. We spend an enormous amount of effort, and we achieve effect size of about 25 minutes. So, meaning that for all the work we do, we take a child who watches 2 hours a day or 3 hours a day and reduce it by 25 minutes. Not a very, very big effect size. Certainly not something that, that you can feel great about. So the question is, are there ways that you can reduce that harm? And are we evolving from this to this, and ultimately, I would say ideally, to technology is being used to engage children in the ways that we already think are good for them. So I hope that I've convinced you that early childhood for children and for mice is critical to their development, and that children need more real-time play and less fast-paced media. Because when you change the beginning, you change the whole story. And you guys are changing the beginning for children, and I can't thank you enough for that. It's the most important job there is. So good luck, Godspeed, and thank you very, very much. I want to acknowledge people. These are people in my lab that do the work. And thank you. I think I have about 15 minutes for questions, if there are questions. Yes.
This is a little bit of a comment.
Yeah.
Okay? In terms of the I did it with the iPad
Yeah.
versus the I did it with the I put all the hair curlers in the jug.
Yes.
The jug scenario includes absolute knowledge of how the thing happened.
Uh-huh.
The iPad is like, even, you don't know what an extreme crowd you're talking to, because we don't even believe in giving babies rattles that they can't see what's the mechanism.
Uh-huh.
So our belief is that cause and
That's interesting.
effect needs to be very, very
Yeah.
evident to
Yes.
the child. What do you think about that?
I like your approach, actually. I think that two things. First of all, philosophically, I don't have any disagreement with you. But I would argue that actually much of what happens for young babies is mystical anyway. They really don't. I mean, cause and effect is a process that develops much later in life than children have a lot of experience to. Truly understanding causality, which is to say that you understand how the rattle actually works, not the fact that you shake it and it makes a sound. Right? That's like level 1 cause and effect. I shake this, it makes a sound. Why it makes a sound is a higher order. And I would argue even the transparent rattle, it wouldn't be obvious to them that it's these balls hitting right. But I don't want to be misconstrued here to say that I actually think these things are good. I only want to make the point that we do have to recognize that they're different. So I took on Baby Einstein. They're still suing me because I think that those programs are horrible, absolutely horrible, have absolutely no benefit. Absolutely no benefit and a real risk of harm. I have to be honest as a scientist that I think that these things are different, that there is a difference in this type of experience for a child and traditionally just sitting there watching a program and doing nothing. I don't want to be here to argue that it's better. I've never said that, and I don't think it is. But I do want us to be cognizant of the fact that there are these very, very real differences. And I have to be honest, I think that 20 years from now, children are going to be reading electronic books. That's all there's going to be. Amazon already sells more electronic books than traditional books. They're much, much cheaper to buy. And as more and more parents get Kindles and iPads, it's going to be a stretch to convince them that you should pay $10 more to get Goodnight Moon in hard copy rather than just reading on your iPad. But what I don't want to be lost is that reading to that child is what's really important. So spending time with the let me give you an example. There's an iPad app that's an Etch-a-Sketch app. Okay, I don't know if you've seen it. It functions like an Etch-a-Sketch, as you might imagine. And you shake it just like an Etch-a-Sketch to clear it. I happen to really like Etch-a-Sketches, although I bet you children don't understand how it actually works. I spent a lot of time trying to figure it out as a child myself, scraping off everything so I could look in and see. And I still couldn't figure it out. It's an amazing toy. But that electronic Etch-a-Sketch, I would still argue because of the differences in tactile stimulation, three-dimensionality, is not as good as an Etch-a-Sketch, but it's not the worst thing in the world either. And if given a choice between them doing that and watching Baby Einstein, I would much rather they did that. That's my only point. Yes. Oh, okay. Microphone people, you just put people on. I won't.
Hi. I have a question for you regarding your thoughts about multilingual children and whether or not, if they speak 2 or 3 languages at home, if that will affect their cognitive functionality later in life?
It's a really good question, and so the early research in children's language acquisition and multilingual experience at home seemed to suggest or initially suggested that they had delayed language. But in fact, the problems with those studies was that they typically assessed language in the one language, not in the other. And what happens with bilingual children is that they, early on, in their effort to try to use language with maximum flexibility, adopt words from both languages that they find more useful. In fact, some of the most interesting studies on this were done in Bosnia-Herzegovina, where children learn both Serbian and Czech, I think. I'm trying to remember what it was. And in one of those, what's that? Russian, okay. In one of the languages, there are words where the verb is collapsed into the noun. So for one word, you can actually communicate 2 things. And these children would preferentially, because they're limited by their number of words, right? They progress from 1 to 2 to 3. They would switch so they could get much more usage out of the language that would allow them to combine more meaning. So the short answer is, or the long answer at this point, there's absolutely no detriment whatsoever, we now know, that actually the initial language delays, which then went away as children caught up and learned to separate languages, aren't even there in the beginning, because children are combining both languages and they're not assessed with both languages. And there's some people that feel that it actually provides greater cognitive flexibility. I talked about working memory and cognitive flexibility. And if you think about it, that's really training very early on in cognitive flexibility, that you've got 2 languages you have to learn to manipulate and keep in your brain. I don't know that there are any proven benefits, but I don't think there's any harm whatsoever. The obvious benefits are that you learn 2 languages. I was raised, Greek was my first language, and then English started when I was in kindergarten.
Hi, thank you so much for your talk. One of the things as a parent that has been difficult for me is coming to RIE later, and I know this audience is mostly infants and young children, but many of us work with older children too, who haven't always had the benefits of so much focused attention, or not having as much television, or they've already been exposed to so much. And we see so many times about the damages. Is it possible to reverse it, or is it irreparable? Because, I mean, as a mom, we know about mommy guilt. And so I guess I'm kind of looking to see if there's any kind of validation for moms who are changing and doing things differently with their older parents. Do you have any research on that?
So my lab focuses birth to 5, so I don't have personal research older than that. The normal teaching around, I would say that I showed you that the brain development isn't really complete until children are in their early 20s. So there's still a lot of maturation going on, and it's by no means a done deal. There's clearly a lot that can still be done. And in fact, particularly with kids with attentional problems, as they get older, you can train them to specifically develop inhibitory control, to work on that part of their, and many medicated kids as they get older can go off medication because they've learned other strategies for how to avoid distraction. So, and one of the things when I give this, I certainly don't want anyone to, this is really all about trying to create the optimal environment for children over their early childhood, in my case, but really over their lifespan. But it's not deterministic. I mean, it's not as if this explains everything. And, these early, because I have parents say, well, I've done irreparable damage because my child watched Baby Einstein DVDs and they feel horribly guilty. That's not the point of this, because I think that it's not a good thing, but it's not as if it's the only thing that determines what happened, how children are doing.
Hello. So
Hi.
I'm thinking about, as I was seeing the images on the screen of children reading on an iPad or coloring on an iPad, I was thinking about the olfactory learning, because, who doesn't remember what a library book smells like, or what a crayon smells like? And when I pick up a crayon now or play with Play-Doh now, it takes me instantly back to my childhood.
And so I know that there must be additional learning and synapses firing around olfactory sensations, as well as when you color on paper or on canvas or on cardboard, it's always a different sensation that you're
Yes.
feeling there.
Yes.
And I worry
Yes.
when we're all just coloring with our fingertips on glass. you know.
It's an excellent point. So Proust himself actually said that olfactory memories are the strongest, and you're absolutely right. So like a smell can take you back to a very, very specific place, even from your childhood. As you said, crayons are an example. The smell of cut grass. There are any number of things that will take you instantly back. It's very, very powerful. I didn't particularly like the smell of magic markers, but you're right that when I started playing with my kids with them, I was like, oh yeah, I remember exactly what this smelled like. They haven't really changed, it seems, over time. Your point is excellent, and I want to reiterate that this Brave New World is not good, but it's less bad than it used to be. I guess that's the only way I can put it. That this is harm reduction. It's not a good thing. And I didn't say this, but I don't think kids should spend more than 30 minutes a day with these, and that's the advice I give to parents, which actually is a reduction from what most of them are doing. And it's about the amount of time they typically would play with anything, any toy in a particular day. So it still leaves plenty of time. And I can tell you the apps that I like the least are the ones that displace a really great existing toy. So, there's this Lego one. And I would hate to live in a world where children experience with block play is this and not this. Because this is not this in many of the ways you articulated. So I think part of our challenge is to think about how do we leverage this technology to do something that is at least harmless and might even be good. So in particular, the issue of joint attention, and most of you are probably familiar with kind of, for example, dialogic reading. Are people familiar with dialogic reading? So dialogic reading is basically, actually Colleen Hubner from University of Washington was, I think, one of the first people to ever study it, but basically it's the right way to read to a child. It seems sort of silly for most people to hear that because there's no wrong way to read to a child, but there are better ways to read to a child. And the general idea of dialogic reading is that, some people call it see and say, that you make a point of engaging the child in the book, that you're not just reading the narrative. And a lot of even well-educated parents who will read to their child will just read. They'll take the book and they'll read it, as if they're reading aloud to themselves. There's nothing wrong with that. I mean, it's always good to read to your child, but there are actually better ways of doing it. And some parents, sort of level 2, will be they ask closed-ended questions. Where's the bear? And the kid can just point to it. The best way to read to the child is to engage the child in the book, to ask, what is the bear thinking? What is the bear going to do? Because it develops not just sort of social interactions with parents, but it also promotes language development. It's shown to promote language development. So traditionally, we tried to teach parents to do dialogic reading. In some of the studies we're doing now, we have a DVD that we push out to parents, that we give to them for them to watch so they know how to read to their child. But could I imagine that an ebook came with sort of prompts to parents to read to your child the right way to promote dialogic reading? Yes, I could imagine that. And, I would argue that that would be good, as long as they're still reading and not just setting the iPad there and walking away.
One of the things that you said you did not cover in your talk was memory, and I was wondering if you had any comments or have done any studies about how to improve a child's memory, in early childhood. What can impact that or affect that?
Yeah, it's a good question. I mean, all of these activities together. So I presented kind of one dimension of executive function, inhibitory control, but they actually they're all sort of interrelated, and they're all grown in the same way. So, to be honest, memory is developed not just in the normal ways we think of it. There's certainly some games that are direct memory games. I mean, concentration, which you can even play with an infant in one form or another, right? You can, if nothing else, you can put something under, the old shell game, right? That's concentration, that's memory. You take a cup, put it over something, move it around, get them to point to where it is, make that more and more difficult. But all of that is the same, it's all executive function, they're all related, right? That child has to be focusing on the cup that you're moving around, right? Not be distracted by the others, not be distracted by where anything else is. So we see all of these things kind of tracking together. That's really why they're the three cores. I focus on inhibitory control because it put it in the context of the larger picture of what we see over the lifespan and how self-control developed in childhood is so important. But they're all very important, and they all develop in much the same way.
Hello, thank you. I have, my question is there any plans to study the iPad use long-term? Is that going on now, or is that planned in the future?
So, yeah, thank you for asking. So we are in the process right now of trying to study the iPads. And part of the frustration for parents is that as a researcher, I can't keep up with the explosive pace of technology. So the iPad, as I said, had been around 4 years. So in my lab, we rely on federal grants to do research. In the old days, it took us about 8 months to put together a grant proposal. It took us a year to get it funded from the NIH. And then it took us, let's say, a year or two to do the project and a while to analyze it. It is so hard now to get money, federal dollars anyway, to do research that it's taking longer still. We're in the process now. We've actually applied for research grants to study iPads. We are studying them already in a provisional way in our lab. And we're replicating the experiment I showed you using TV, now iPad, and blocks. And my prediction is, my hypothesis is that we're going to see that the iPad is closer to blocks than it is to TV. It's not going to be all the way there, but it's going to be closer to that. So yes, we are studying it. Others are too. It takes a long time. And the truth is, by the time I'm able to tell you what iPads do, it's going to be passé. There's going to be holographic, technologies here, and no one's going to be using iPads in 5 years.
Hi. I'm over here. I know mostly you deal with technology, but I wonder if any of your tests have had to do with nutrition or anything, just because the brain and the gut are so connected, and there's the ADHD topic, the low income, and autism and all that.
So I don't study, it's funny you say that. So I don't actually study, I study everything, not just technology, that affects early childhood. Nutrition is incredibly important to early childhood, particularly to brain development. And we see this especially in the developing world. Iron deficiency early in life, micronutrient deficiencies early in life has long-term, irreversible, for the person who asked, effects on cognition. So it's incredibly important. We don't see that as much in this country. Now there's a lot of excitement over what's called the microbiome, which is a little bit different than just the food you eat. It's the bacteria that live in our guts that are affected by what we eat and where we live and how clean we are. And I think that's an emerging area of science that's incredibly interesting. So not directly related to nutrition, and we're doing some work on that right now, looking at how the intestinal flora of children impact actually specifically now we're looking at obesity, because there's some reason to believe that the microflora of the gut impact obesity in childhood and adult life.
The synaptic connection slide that you showed is sort of compelling as a parent of a newborn and a 3-year-old. It's sort of, obviously, then there's sort of the 15-year-old pruning. And I know that's normal, but something it activates some sort of mama bear instinct of okay, how can we prune less? So
no, the pruning is good. Pruning is good as long as it's done in the right way.
So is all of the pruning, is it all in this situation where you have a dual language household, or you're sort of exposing your child to more stuff, is there less pruning? Like if it's a kid who's
No, so the pruning, so it's a very good point. So the initial, I said before that every experience an infant has creates a synaptic connection starting early in life. So and there's no discrimination to it. It's everything, okay? And there's hopefully a lot of good kinds of stimulation. There's a lot of, or some bad stimulation. There's some irrelevant stimulation, okay? Yeah. But it gets fine-tuned. I don't think of the pruning as bad. Think of it like pruning a tree. You can prune it well or you can prune it poorly. But the process happens anyway. You want to have reinforced the right connections, right? You make a lot early on, and then you gradually trim the ones that aren't being reinforced because they're not needed anymore. So
what's an example? What's an unnecessary connection?
Well, it's hard to provide sort of a real-world example, but provide sort of a theoretical one. So all of the experiences that a child is having early in life that are causing these synaptic connections with every single interaction, those eventually go on to develop higher-level connections. So in the rattle example we used before, every time they're hearing the rattle, it's making a connection. But eventually they start to learn, they make the connection between the rattle, moving it, and the sound it makes. And they don't need all of these other connections that were purely reactionary to hearing the sound and seeing something move. They've started to create sort of a cause and effect association, and they don't need to have that anymore. When you're learning to ride a bicycle, okay, use that example, all of those, every action you're having is creating connections. Most of those aren't right? Most of the early experience riding a bicycle is creating connections that are frankly wrong, right? You don't need those anymore. Now you know how to ride the bicycle. These things, the time you fell down isn't necessary anymore, right?
So I can tend to be very extremist, and I'm trying to not be extremely extremist with the TV thing. Is there